to talk a little bit because Koju has already have a nice introduction about how we learn chemistries in the lab. And now I'm going to bring those chemistries into space, not just only into our own galaxy, but also galaxies outside of our own Milky Way. So my title goes as Alchemists. We play no magic, but we play chemistry in space. In short, we call it astrochemistry. So these two nice maps gives us, like a kind of a place where we imagine when chemistry happens in our own galaxy, in the dark clouds, and we extend our imagination outside of our Milky Way. So, alright, so I consider this meme as my personal best so far to summarize what we observers are doing chemistry in space. So first of all, we need a bit of photons so that we can observe them from the ground. And we need 3 spoons of molecules. You can imagine water, CO, or alcohol that Koju just mentioned, and multiple flavors of alcohols actually. And the third, we need some astrochemistry, that whatever that is, because it involves a great complexity when we allow molecule particles to interact with each other. So that brings up a full ecosystem of like when they interact with each other and born or produce new flavors of molecules or destroy and break things down into whatever that is. So, wrong direction. So if we combine the first two, if we combine the photons and molecules, when we allow photons and molecules interact with each other, what we see is that I summarize here in a little green circle here. That is the photons we observe in different colors. So by different thickness, I want to emphasize their how bright those photons reaches our eyes. So by receiving these different flavors of photons, different colors of photons in different intensity, using, for example, ALMA, which is one of the greatest instruments in the world that I use, so we were actually able to, by using these different colors, we were actually able to magically infer back their environments. So, for example, if you take a snapshot over someone's table in an arbitrary corner of the world, you can see on this table there are different kinds of drinks. So you can picture like maybe they, like nice iced tea as the blue light I picture in the green circle, and the red hot tea as another color of light. So by picturing this table, you can start to imagine, oh, this must be very hot, summertime. So by taking this similar idea, we, by collecting different colors of photons, astronomers could magically infer back how hot environment is. So our table or our snapshots could be galaxies that I pictured here, or any kinds of interstellar space. So if we're combining the latter two, combining molecules and astrochemistries, we basically allow them to interact with each other. Like I said, it could bring out production, it could bring out destruction. A good example for that is that we could actually use different flavors of molecules to differentiate the environment. For example, in the very extreme environment like shock environment. So, for example, in the environment where fast shocks are greatly influencing, by fast I mean 60 kilometers per second. 60 might look like a very small number, but if you wrap around your head around this is more than 10 to the 5 kilometers per hour. That's a crazy car driving through space. In this fast shock scenario, that this shock could be a heavy kick that kicking out silicon molecule inside the very core component of the dust grains that Koju just mentioned, and release this silicon molecule into gas. And this silicon free into the gas phase, then can form silicon monoxide in the gas phase, so that we are able to observe the interaction of photons and the silicon molecules that reaches our eyes. So in essence, in sum, if we observe silicon, it has great chance that is coming from the fast shock environment. On the other hand, if we're thinking about a slow shock, 20 kilometers per second, still really fast if you again, do your math. But in this much slower shock, we also expect to see another flavor of molecule that we call HNCO. So in this scenario, that the shock is effective enough, but not fast enough to destroy this molecule, it's a much gentler kick that will drive this molecule to leave the grain surface, and then again, interaction with photons, we ALMA observer claim our victory. Another scenario that we are able to see HNCO, the second molecule I just introduced, is through we call it the thermal sublimation, when the temperature is high enough and the interaction between the gas and dust are still coupled. That in this scenario, that you don't need shocks basically, but you are able to still see the HNCO through telescopes. So these are the chemistries when we think about molecules and chemical reactions. So what we do as an observer using ALMA, such a great instrument, is that, like I said, you have different snapshots. You can see, take a snapshot of people's table or a snapshot about their outfits, that you can start to guess, oh, it's hot, but it's somewhere hot. Is this, by the beach, the seashore, like Spain, or someone else's garden, for example. So that's why we need different flavors of molecules. We want different kinds of snapshots to have the full story, to tell the full story, instead of just gazing at one picture and make up our own story. We want the true story. So Alchemy is ALMA. It's a large program using ALMA data. It has tons of hours of observations to produce a massive amount of transitions or photons observations from tons of molecules. So we can play different sets of molecules because they arise from different interesting chemistries. They have different transitions that we were able to infer, for example, their temperatures or other physical properties. So so back to this need. How do we play using our data? For example, in brief, this plot summarizes that what are all the physical conditions we could infer from our observational data. So taking this black square out, this is a temperature profile that we can infer from these two flavors of molecules. So if you only combine the first two parts, we can see that, these two molecules are tracing different temperature. SiO, silicon monoxide, is tracing very high temperature. So maybe it indeed comes from the shock heating, for example. But what about HNCO? If we only have first two parts of this meme, then the story will end here, like they're just tracing different stuff. That's it, end of story. But only if we are including the final bits of astrochemistry, it is actually for HNCO that at least at this really low temperature, like 50 Kelvin, we observers then have to knock on the door of Koju's office door, like, hey, what does this temperature mean to us? We don't know, we don't understand. Can your lab results tell us something? So actually from some of the paper, it seems like this temperature is not hot enough to sublimate, to release the HNCO from the dust surface into gas phase. So this must coming from shocks again. So these two flavors of molecule, they are tracing very opposite end on this distribution of temperature. They're very extremely different, but they both need shocks. And this part only can come into our knowledge until we include the astrochemistry bits. And the second part of this, they both need shocks, but from the chemistry that I just talked, they come from very different shock scenarios. So they could come from the same shock episode, or they could come from, like a very randomly distributed. So this come in, when this part come in, then we can have a more comprehensive picture and then continue our story. So I think, to conclude, what we are doing is that we are collecting bits from photons, bits from molecules, and how they interact with each other, which is chemistry bits. We alchemists, because this large program comprises of a lot of observers, a lot of astrochemists, and a lot of physicists are working on this. We all alchemists are going to continue this exploration because you see the crazy spectra I just showed involves tons of molecules. So we're working on it, and we cannot we cannot wait to show more in the future. So I'll stop here and I'll start taking questions.
Anyone?
Maybe I missed it, but what are the sources of the shock? Are they supernova explosions or something else?
That's a good question. So maybe I'll stay in this galaxy. So that profile actually comes from this galaxy. Sorry. Okay, I have a pointer. So this galaxy is almost adjunct, and from other observation, we see a massive outflow that's potentially driven by very fierce activity of star formation. So fierce enough, we call them even starburst. So this very energetic activity could start to interact with molecular gas in the ambient environment and create shock regions. So for this galaxy, it could potentially be from the starburst activity. But in different environments, in another galaxy that I study, it could from another source like AGN activity, which is also driving energetic outflow, but it's different source, but still energetic episodes in different galaxies. So thank you.